My name is John Hay. I'm with the University of Nebraska Lincoln Extension, and I work on energy and biofuels here. And we host this web seminar the last Friday of every month on bioenergy and renewable energy related issues. And I'm pleased to have Dennis Pennington with us today. Dennis is a bioenergy educator from Michigan State University, and Dennis has an exciting project going where he's been growing a number of different crops throughout the state of Michigan for a number of years. And so we're going to get a really neat view of a variety of bioenergy crops and the success and failures he's had through those different trials. So I'd like to welcome Dennis Pennington to discuss bioenergy crops for Michigan and the upper Midwest.
All right, well, good morning, everyone. Like John said, my name is Dennis Pennington. I work for Michigan State University Extension. I'm a senior bioenergy educator here. I've been working for Extension for about 15, going on 16 years now, in the last 7 of which I've been working specifically on bioenergy crops. And my background is in agronomy, so a lot of the stuff that I'll present today have to do with how do we grow these energy crops. And what I guess my hope is that I can be in a position when we see these cellulosic ethanol and bioproduct facilities take off, I can be in a position to help farmers make decisions about what should they plant, what kind of fertilizer applications do they need, what's weed control issues, and some of the production practices that they might need on their farm. So that's what I will kind of focus on today. I've got to help accomplish that, we've set up here in Michigan a kind of a network of biofuel productivity plots. So we have on-farm as well as on research station properties, research plots where we're just evaluating different energy crops. You can see from the map there, we've got them kind of geographically spread across the state. We've got 11 counties. At one point, we had 21 different counties involved in some different types of projects, but that was a little hard to manage, so we backed it off to 11. But we've got them spread across the state so that we can identify, what type of crops might produce best in each region. In order to do this, there's been quite a few funding partners involved, and I just wanted to recognize those. They are listed on your screen here. It takes a fair amount of money and time to buy the equipment, but then also to travel to all these different sites, taking tillage equipment, planting equipment, harvesting equipment, and whatnot. So I appreciate the funding partners that I've had on these plots. So the crops that we've had in some of these research plots, I'll list those here. In terms of perennial crops, we've got switchgrass, miscanthus, Indian grass, and we've got some big blue as well. We planted prairie cordgrass one year, and it really didn't take very well, and I've not tried to reestablish that, although I think D.K. Lee may have some new strains at University of Illinois that I might be more successful in planting. And then, and those are all warm season perennial grasses, and then the last one on the list, the reed canary grass, is a cool season perennial, and there are some livestock farmers that have used reed canary grass in low areas for grazing. So there was some interest in planting reed canary grass, so I had that planted in the plots for a little while as well. In terms of annual crops, the reason why I included annual crops here is because I think the initial transition to get from where we are today to farmers planting bioenergy crops and supplying them to a biorefinery, we may need to include annual crops as transition crops to get there. So the annual crops that we've been looking at include corn and 3 different types of sorghum. The sweet sorghum has high sugar content in the stalk, and then there's 2 different what's called energy sorghums, and those are being bred for higher biomass. There's a photoperiod sensitive and then a non-photoperiod sensitive energy sorghum. I'll talk a little bit more about them a little bit later. Then we've also looked at some oilseed crops that would be used for making biodiesel. And I see I didn't fix my slide here. The oilseed crops that we've planted here include canola, oriental mustard, camelina, and pennycress. So we've actually been planting those, and we've harvested, and we've been actually making biodiesel in a portable unit that we have on farms canola oil. So most of the focus has been on the perennial crops, some a little bit focused on the annual crops, and then with probably a little bit less on the oilseed crops. I'm not going to get into a lot of the details about each individual crop in terms of the cultivation and the production practices. What I'm going to do is share with you more the information from the research plots that I have. If you want more detailed information about each individual crop, there's a good series of articles on the E-Extension website. I was part of a feedstocks team, and looking through the attendee list here, some of you, I think, were part of that group and helped actually write or review some of these articles. So if you go to the E-Extension website, that's listed up here at the top, and you should be able to click on Ag Energy. When you get to Ag Energy, you should be able to get to the feedstocks for biofuel production, and you'll find probably, I think, about 18 or 19 different energy crop profiles there. So get more information there, more detailed information there. Now, because we're planting perennial crops, annual crops, some of these you plant early in the spring, some of them you plant later in the spring, and then the harvest time is all different. There's a whole variety of different ways that we have to plant these crops because I'm trying to do it not at one farm, but take this out on the road and travel to all 11 of those counties that you saw on the map. So you can see from the pictures there's kind of a variety of different ways, from broadcasting seed to the little Planet Junior planter to even hand planting, and as well as drilling seed into the ground. So trying to conduct these plots in the geographic distance between them that we are kind of creates some challenges. Normally we would mechanize the planting of these crops a little bit more if it was on a farm and we're going to plant a 100-acre field. But for these plots, a lot of this is done by hand and with small equipment. One of the caveats, and you're going to notice this when I start sharing some of the data, is the drought that we had last year. This is a drought monitor index from UNL on August 7th, and it shows the gradient of drought from severe down in the southern part of the state all the way up to, abnormally dry, or even some places in the UP that were normal conditions. And so some of the effects on drought, if you notice, this is a plot of switchgrass on the left, miscanthus on the right, and notice the top of the miscanthus. You can see it's turning brown, and as well as at the base of the stalk, it's turning brown. That's not translocating nitrogen, that's water deficiency. And I was a little bit worried about this miscanthus because the top was really starting to die back, and but it did later on in the season. It did come out of that a little bit, and it did put up some green shoots growing there. You can see it's still brown a little bit at the tip there, but the drought in several of these locations had a significant impact on yield, particularly on miscanthus. This is a plot of, on the left here, of Indian grass, and you can see I've never seen a warm season perennial grass curl up like corn leaf does. You can see the corn on the right here, but the Indian grass actually, in the big blue stem also, curled right up in response to the drought to try to conserve as much water as possible. Other problems that we've had, we plant these plots in small plots scattered around the country. We've had wildlife damage, which have hindered some of our corn yields. This picture is frost damage on some switchgrass. This was in 2012, where we had a really warm March, and the switchgrass came out of dormancy, and then it was followed by several periods of killing frost. I don't know to what extent this impacted yield, although I do know that the switchgrass did survive, and I did get, I would say, relatively decent yields, keep in mind the drought conditions that we had. Other conditions, this is lodging in sweet sorghum at one of the locations in 2010. Initially, when I started planting sorghum, I thought that I needed to plant on narrow rows, and mostly because if you look at sorghum, I grew up on a dairy farm, and we planted sorghum as kind of an emergency forage crop, and you'd go out and chop it, 3 or 4 times throughout the season, and that's how you got the most tonnage. Well, if you're letting it grow like I was intending to do here, planting it in narrow rows just does not work. All it takes is a little bit of wind, and that stuff goes down. Another thing that I learned in terms of lodging is the difference between big blue stem and Indian grass. Big blue stem really does not stand up well if you harvest it late in the season after killing frost. I've had lodging problems with big blue stem on every plot that I've had. Now, if you get in there and harvest it while the plant is still green, you can avoid that lodging problem, but the benefits of translocating nutrients to the roots are missed when you harvest early. So the lodging issue with big blue stem for me has really kind of made this not even a contender. It's a decent yielding grass, but in monoculture, the way it's planted here, you can see the difference between Indian grass and big blue. It's probably going to fall out of the mix as far as a monoculture crop. Now, if you mix big blue stem in with Indian grass and switchgrass, maybe the lodging will be less of an issue, but that's been a real problem for me in these plots. Weed control. I'm planting some crops that really don't have much in the way of registered herbicides. There are registered herbicides for sunflowers, but as you can see, my experience with growing sunflowers is minimal, as is documented by the weed problems or weed pressures in here. But controlling weeds in miscanthus and switchgrass, there's not a lot of, as well as the oilseed crops like canola and oriental mustard, there's not a lot of labeled herbicides that can be used on them. So we've got some work to do in terms of the weed control. So let's move on to some yield data. And let me just give you the grand perspective, the overall. This is a summary of all the plots I've had over the last 5 years. And this is for the perennial crops. So in this chart, you can see the first column is site years for each of these crops. And you can see some of these I have only very few, and some I have quite a few, like switchgrass. I've got 32 site years. And the way I define a site year is I have 4 replications at one site for that year. That's considered one site year. So actually with switchgrass, I have it planted at 8 locations. I have 4 years worth of data. So 4 times 8 gives me the 32. So the next column is just the units, and this is all reported in terms of dry matter tons per year. On these perennial grass, I broke this down into year 1 yield, year 2 yield, and then year 3 and 4, indicating that year 3 and 4 would probably be what I would consider close to a mature yield or mature stand established. And then the overall average yield is just the average over the number of site years for each of the crops. The last column is ethanol, and this is calculated in terms of 85 gallons per ton. Some might argue that number is a little low, some might argue the number is a little high, but 85 gallons per ton is what I use to calculate this number in this last column. So what's interesting, typically you would think that you're going to start in year 1, and let's look at switchgrass at 1.77 in year 1, 4.78 in year 2, and then year 3 and 4, it held steady or even declined just slightly. The reason that it declined slightly is because of what happened in 2012 with the drought. And notice what happened to Indian grass and big blue stem. It significantly dropped off in year 3 and 4, and that is mostly due to the low number in 2012 due to the drought. So miscanthus is another thing that you might want to look at. The first year yield averaged 2.31. By year 2, we're up to 5.58. Year 3 and 4, again, 5.07 was the average yield in those in an established stand of miscanthus. But if you look at the overall average, I'm at 4.45, which is probably half of where I really should be. So I do have some individual plots and individual locations where I've seen 8, 9, 10, and even 12-ton dry matter yield per acre on miscanthus, but that has not been the overall average if you figure in all the variations in soil types and climate conditions across all these plots. So there's been some really large numbers reported as far as yield potential for miscanthus, but I'm afraid they don't figure in that establishment period and the variation. That's a number that comes from a fairly small area on some replicated, research plots. So, does anybody have any questions on this overall data before I move on to the annual crops? I see a question here from Gene. Will Arundo Donax survive in the upper Midwest, and how far north? I don't know the answer to that question, although that is a crop I wouldn't mind at least putting in a plot to try it and see. It has some significant yield potential in the south, but I honestly couldn't tell you how well it'll do the farther north you go. Any other questions? All right, let me move on. This is annual crop yield. This is laid out in a similar fashion. Notice the units here are a little bit different for corn. I've got bushels per acre, so this 126 bushel yield is over 15 site years. That's not anything to write home about, but you look at where we're planting these crops at, and we're planting it on some fairly marginal sites. So I guess keep that in mind. Corn stover yield, we've got 14 site years worth of data. The average yield on that was 3.12. And if you look at the harvest index, which is kind of a measure of a comparison between the stover and the grain, we're at about a 0.54, and 0.5 is kind of the generally accepted average. So we're fairly close as far as that goes. You see your ethanol yields over on the right. And I'd like to highlight the sorghums. The forage sorghum actually did as well as the miscanthus, although I think miscanthus has a higher yield potential, and plus you have the benefits of it being a perennial crop rather than annual. But look at the energy sorghum, the photoperiod sensitive stuff, and then the energy sorghum. You're getting 8 and 9 ton dry matter yield, which translates into more ethanol per acre than any of the other crops that we've been looking at. Which, in the end, that's really what where we're headed. And I think these sorghum crops would fit on most farms that are growing corn now, because the equipment you plant with, the way you would harvest it, that equipment is fairly readily available. And plus, you're only committing your land to an energy crop for that 1 year, as opposed to planting a perennial crop where you're planting it for, it could be 5, it could be 10, or even 15 years. It's more of a long-term commitment. So, overall, oilseed crops, I've got Oriental mustard, camelina, and canola. You can see I have less site years. As I mentioned at the beginning, we've put kind of a little less emphasis on those crops. In the yields, they're probably a fourth of what they really should be. I would like to see those yields pushing 1,600 pounds per acre instead of 400 or 500 pounds per acre. And you can see in the right column that doesn't translate into a whole lot of gallons of biodiesel. So we've got to figure out a way to be more productive. We've got some farms that are growing canola that fertilize for 60 bushel yield, and in this last year they got 42 and 45 bushel yield, which is pushing 1,800 to 2,000 pounds. So there's some potential there, but it's going to take a little more input than what we've been putting into our crops. And plus, this is on some marginal land. We're putting 130 pounds of nitrogen on, and I'd have to look. I want to say it's around 30 pounds of P and K on each of these crops. So in weed control on some of these has been an issue. The canola we generally plant Roundup Ready, so we generally get pretty good weed control in the canola, but we've had trouble with the other two. Question on the oil seeds, is this fertility or weeds, and why so low? I think I just answered that. John, the question on winter or spring, this is spring canola. We have planted winter canola in the Great Lakes Bioenergy Research Center plots for 4 years. All 4 years, we've had to replant with a spring variety in the spring just because it doesn't overwinter. For us, we have to plant the crop so early in the season that it doesn't even fit behind a soybean rotation or a soybean crop, or even after corn silage. We have to plant it in August. So the only crop it could rotate after for winter canola would be wheat. And we have not tried that. And Gene, yeah, your comment about sulfur, canola does like sulfur, so that's something that we will probably be adding to the mix this year. All right, on to the next one. Energy sorghum. These are images of the energy sorghum. On the left is the non-photoperiod sensitive, or just kind of the standard. And you'll notice in this the seed heads at the top of the plants, and compared to the other picture where you don't see any seed heads up here. What makes this sorghum on the right different is it is photoperiod sensitive, whereas on the left it is not. And by photoperiod sensitive, that means that it doesn't trigger flowering until the day length gets below 12 hours and 20 minutes. That doesn't happen in Michigan until about the middle of September. So this photoperiod sensitive sorghum over here on the right just keeps on putting up vegetative growth. The stuff gets really, really tall. Now, when I figured the total dry matter tonnage on these, I added the seed head on the left. So maybe I should have segregated that and evaluated just the vegetative yield. And if I would have, the energy sorghum, the photoperiod sensitive, would have yielded a lot higher. But you can see that when you add that seed head in here, 10.9 tons compared to 8.5, it still yielded more. But let me show you another picture. This is sweet sorghum on the left, energy sorghum in the middle, and then the photoperiod sensitive. You can see this photoperiod sensitive. Look at the size of the leaves and the number of leaves, and it just keeps on growing and getting taller and taller. In order for me to measure the height of them, I actually had to cut a plant off and lay it on the ground so I put a tape measure next to it. It just got so tall. So I think there's some potential for these energy sorghums in terms of being kind of a transition crop for farmers that may be willing to commit their land for a year or 2 years or 3 years, but they want to know that the market will develop and they'll have an outlet for their biomass before they plant any significant acreage to, say, switchgrass or miscanthus. All right, next plot is a Miscanthus Establishment trial. Some of the data I'll share here is a little bit contrary to what Emily Heaton has found. There's a little bit of differences in the experimental design between the two, and I'll try to make sure I highlight that so that we're clear on that. The purpose was to compare transplants that were started in a greenhouse to planting bare rhizomes, and this is in a non-irrigated soil, so we didn't add any water or any irrigation to it. So the treatments, we've got the M root, which stands for the bare root, and then the M trans, which stands for the transplant, and these were plants that were transplanted live in the field after 8 weeks of growing in the greenhouse. So this is what the bare root or the rhizome looks like. That's the Sharpie marker next to it, just so you just get an idea of the size. When you plant rhizomes, you want to make sure that they have a live node. You can see that these are a couple of pretty decent ones. These got 2 or maybe even 3 live nodes on them. And this is what the transplants looked like. They were in 4-inch square plastic pots that we transplanted in the field. So a fairly sizable plant that we knew was viable and that was already growing. So the comparison is between the live plants and planting these bare rhizomes. First set of data is mortality, and this is death, basically. And you can see the blue is the root, so the bare roots. We had almost 30% mortality initially in the first year of planting. I thought, well, is there any chance that might come out of dormancy or something? And you can see by year 2, we didn't see any improvement. We didn't see any rhizomes that were planted that just grew next year, and that held through even through the third year. But the other thing to look at, your transplants, we had zero mortality. Every one of those plants survived in this plot. So the next thing we looked at is the number of tillers per plant. And essentially what we did is we took each clump and counted the number of stems or tillers that were growing. And we tracked that number over time. And you can see that in the first 2 years, the red, the transplants were significantly higher in both of those 2 years. But then look what happened once we got to the third year. The rhizomes, the bare root, actually had a few more tillers. So by the third year, it was able to overcome that, and it had the same number of tillers per plant. So the next thing that we looked at is the dry matter yield, because that's essentially where it's at, and what we're most interested in. And you can see, of course, the trend is pretty easy to follow here. The transplants did better in 2009. They did better in 2010, and they, even though the roots had more tillers per plant, remember there's 30% less of these plants. So the transplants actually yielded more, and then in 2012, look what happened. Our yield was about half, or just a little less than half of what it was. And I would expect, if the trend was to continue, I would expect these numbers to be up here at the 10 or possibly a little bit higher. But our drought conditions that we had, you can see, had a very significant impact in 2012. So if you add these all together, and you look at the total yield, the rhizomes yielded 13.8 total tons over that 4-year period, and the transplants yielded 20.4. So the drought had a significant impact. I'm hoping that things will respond okay in 2013, and we won't see our mortality go up or the number of tillers per plant decrease. But this is a 6.6 ton per acre increase in yield, and so that's a pretty significant yield increase. Now, the work that Emily Heaton did used smaller transplants. These were like plug transplants, and her analysis showed that the yields were about equal for them. And so if the yields are about equal, and you don't have the cost of growing the plant in the greenhouse from a dollars and cents standpoint, you're better off to plant the bare root. So I've got some questions coming in here. Zane, your question was, this trial on good soils or marginal? I would classify these as marginal mostly because they were pretty sandy and very, very almost excessively well drained. And you probably know that Miscanthus uses a lot of water. And the more water you have there, the more production you'll get. So these were actually at the Kellogg Biological Station near Hickory Corners. Next question from Gene. Sources for Miscanthus transplants. There's a few places you can get transplants. There's Speedling out of Florida that propagates those, and you can buy the transplants. And then the question, what's the cost difference between the roots and the transplants? I haven't priced the difference between them. I don't know what the transplants cost because we actually just grew them in the greenhouse ourselves. But this year we were able to buy rhizomes for 27 cents a piece. We bought, I think, about 20,000 rhizomes to plant some plots. So the cost of the rhizomes are going down, and with that in mind, we're probably going to get to a point where, transplanting live plants into the field is probably not going to be cost effective. And I see, Shelley, that's your question about cost analysis, the greenhouse versus the bare root. As we're able to produce these rhizomes in a lot larger quantity, there's equipment out there. The Missouri Farmers Association, or MFA, had submitted a project. They were one of the first BCAP projects accepted. In fact, I think the only ones that were planting Miscanthus. and they have equipment to dig the rhizomes, divide them, and then plant, and it's all mechanized. So I think we haven't actually run the cost analysis for this specific project yet, but I think in the long run, we're probably going to be more cost-effective planting the bare roots. So if there's no other questions about that one, and I don't see, okay, before I go, Gene, if you harvest rhizomes, does the field recover and need to be replanted? You will get some recovery, but you will need to replant. What few little plants survive after you dig a nursery will not be enough to reestablish itself. So essentially, you'll need to plant a nursery, you dig it, and then you spread it out to larger acreage, and then you're going to need to replant your nursery again. So let's switch gears a little bit and move on to the Switchgrass agronomy trial. We've tested 8 different rates of nitrogen from 0 up to 175 pounds per acre. And also this was done in a split plot design where we looked at 2 different harvest strategies. Harvest strategy 1 was a 1 harvest in the fall, 2 weeks after killing frost. Harvest strategy 2, we had 2 harvests. The first one was taken in July, and the second one was taken 2 weeks after killing frost, the same time as the H1 harvest. So this is what the plot looked like, and you can see from here we've got each of the colors represents a main plot, and then each main plot was split in 2. So like here you can see you got an H1 and an H2. The H2 was harvested twice this end, and notice they're all blocked together, and that was to avoid driving on top of this one because this was only harvested once. So essentially in July we came in and harvested each one of these plots. We pulled it with a harvester, harvested it, backed out, went to the next one, harvested it, backed out, went to the next one to do our 2 harvests. And each of these colors represents a different nitrogen rate. So let's look at yield. So we've got the harvest 1 and then the 2 harvest down here. Yield on the harvest 1, 3.64 tons per acre. And then in July on the 2 harvest, and this is only 1 year's data, and I didn't put the year up here, and I think this was 2010. The trend is the same, that's why I didn't change it. The second year, or the 2 harvest system, we had 3.3 in July and 1.55 in November. So if you add those together, the 2 harvest system yielded 4.85 compared to 3.64. I don't know that that's going to be enough to warrant doing a 2 harvest system. You can see the moisture content was quite a bit higher in the July harvest, although we have decent weather for drying at that time, so if we want to put up baled or dry hay, we should be able to get that dry, and that shouldn't be an issue. Now, having 22% moisture in the fall is difficult because trying to dry hay in November can be a challenge, if not almost impossible. You almost have to let it lay out there for a long time. So now the difference between the 4.85 and the 3.64 has varied from year to year, but generally a 2 harvest system will yield more, and it's probably mostly dependent on how much rain you get after the July harvest. That's probably been the key to how much we get in the second harvest. So yield response to nitrogen. The blue line is the single harvest system. The red line is the 2 harvest system, and you can see the numbers that go up on the axis here for pounds of nitrogen, and then the yield on the vertical axis. And you can see that it kind of gets up to a point, and then it starts to taper off in terms of our yield, which is about what we expected. Similar response curve to what you would see in corn. On the 2 harvest system, we got some rain, which kind of spiked our yield out here a little bit, which is not a normal thing that we would have expected to happen. Typically, we would expect that the curve, would be kind of bell-shaped and it would taper off or level off the higher you go in nitrogen rate. So about where we kind of expected to be in the 50 to 75 pounds per acre is about where our maximizing amount is. And if you apply economics to it, probably in that 50-pound range is about where our economic maximum response to nitrogen would be. All right, on to the next study. One of the things, because Michigan is got quite a diverse, not only land cover, but different soils and even climate from going from south to north, we decided to specifically set up plots that would give us kind of what we called a latitudinal transect, and it's to evaluate crop suitability in each of the different regions of the state, crop production regions. In the north, we tend to have, if you take the top half of the mitten and the upper peninsula, that's dominated by forest cover and forest industry. There is some agriculture and there are some row crops produced up there, but it's predominantly forest. So we had these same crops planted from north to south, and then we're just trying to evaluate, are there different crops that might fit better in the north or the south. So what this chart shows is 2012, 11, and 10 for Miscanthus, Switchgrass, and sweet sorghum. And the counties are arranged on this chart from south to north. So north is on the top of the chart, and south is on the bottom. And the red numbers are the lowest number for each crop in that year. The green number is the highest yield for that crop that year. So you can see Miscanthus here at Ottawa County in 2012 yielded 7.6. Up in Antrim County, which was the farthest north that we have Miscanthus planted at this point, yielded only 1.47. So there is, and if you look at the trend here, Switchgrass, 2.92 was the lowest yield in Antrim. Now we do have it planted in the Upper Peninsula, in experiment station there, and the Switchgrass is doing fairly well up there. The highest yield was 5.74, and that was in Saginaw, kind of middle part of the state. Remember that we had drought this last year. In the northern half of the state, if you remember that drought index monitor, the northern part of the state, probably from about, I would say, the Ottawa north, we had less drought pressure than what we had in the south. So I would normally expect that the highest yield for Miscanthus and Switchgrass to probably be more in our southern sites, but that didn't happen in 2012. So, you know, the trend was similar in 2011. The more northern sites had lower yield. The southern sites had a little higher yield. And the Switchgrass, the highest yield down here, was actually in Cass County in 2011. In 2010, we had sweet sorghum planted at 4 sites. And I'm not sure if there's much of a pattern that showed up here or not. In Isabella County was as far north as we went, which is Mount Pleasant. That's about mid part of the mitten. So, switchgrass establishment and weed control. When we first started planting switchgrass, we thought that we really needed to be as ecologically sound as possible and try to establish these crops with as minimal inputs as possible. We didn't fertilize in the first year, and we didn't use herbicides in the first year. So what I did is I took some data, and this wasn't really set up as a research trial per se. So all this is kind of a collection of data with different management practices applied to it. So we've got 2009, 10, and 11, and we've got several locations, 6 locations where we had switchgrass planted. And the stars indicate that these plots in the establishment year were mowed at least once, and some of them were mowed twice. Now, because we mowed them to control weeds and we did not use a herbicide, there essentially was no yield to be taken in the first year. So that's why we have a star here and we don't have a number for yield. Now, in Isabella and in Saginaw County, we actually used herbicides to control weeds, so we actually had a harvest in the fall. And the number that's reported here was our yield for those numbers. The next column is 2010 yield and then 2011. And in the last column, you can see the total yield over the 3-year period. Now, if you add these together, and you take the average of the herbicide treatment, now remember there's only 2 of those. The average yield was 12.93 tons per acre, and this is again in dry matter. And if you take the average of the mode, where we had 4 locations, the average is 9.4, which gives us an increased yield of 3.475. That is enough to cover the cost of weed control in here, and it would definitely be worthwhile controlling the weeds. Zane, your question on the cost of quinclorac, I haven't had to buy any in the last 2 years because I've been able to get it donated. I used to know the cost of that. I may have to look that up and get back to you. But that would be certainly a factor to figure into here. But, you know, even at 3 ton, if you just take a 3-ton yield advantage, at even put $50 a ton on there, you've got $150 per acre of extra income to cover the cost of herbicide. That will more than cover the cost. The next trial I wanted to share with you, and I'm getting about toward the end here, and I know we're getting close to the end of our program here, is a switchgrass variety trial. And this is data from 2000, the trial was started in 2009, and I've collected data up through 2012. Now, one thing you'll notice here is that I've only got data published here for 2010, 11, and 12. The reason is because when we established this, we mowed for weed control in year 1, so we didn't take a harvest on this data, or harvest on these plots in the first year. So this just shows you the different varieties across the bottom, and it's kind of a cumulative yield. I've got the years stacked on top of each other here. So Blackwell and Cave-in Rock, you can see, and this is at the Kellogg Biological Station near Hickory Corners in Michigan, kind of southwest corner of the state, have been the 2 highest yielding varieties, yielding in the last 3 years here over 12-ton dry matter yield per acre. And you can see it kind of tapers off from there with these different varieties. I've got a couple of the blade energy crop varieties in here, these experimental varieties. And then notice the ecotype here, the upland, the U, and then the L for lowland. Typically in Michigan, we're far enough north that we wouldn't expect the lowland varieties to overwinter very well, and that over time that those would kind of thin out and yields would be decreased. But they have actually persisted fairly well at the Kellogg Biological Station, and I mean, they're not the top yielders, but they've done actually fairly well. So, if I can go to the next, this is the same data just in a table format. I'm going to kind of skip over this. I'm happy to share this data table with anybody that wants it. Just drop me an email, and I'll give this to you. But if you look at the lowland versus the upland varieties, you combine all the lowland, which I had 5 lowland and 7 upland varieties. This is the average yield for each of the years here, and then the total over those 3 years. And actually, if you look at the total lowland yield, the lowlands averaged overall over those years have actually produced a little more than what the upland varieties have, which was a bit of a surprise to me. So I don't know for sure how far north that will remain true. And I was out putting urea on the switchgrass on Monday of this week, and I did notice that the lowland varieties, they are very definitely very clumpy type grass, and there's quite a bit of space in between those clumps now. So I think I need to keep this trial going and take it out to 5 or 6 years and really see if the lowland varieties can persist that long. And we really haven't had a severe winter here, not like what we used to have. The moderating temperature of Lake Michigan really seems to help us out here. So that could be part of the reason why these lowland varieties have persisted as long as they have in Michigan. So With that in mind, that's the majority of the data that I had to share with you today. Are there any other questions that I can answer?